In 1977, John Backus, who helped invent Fortran and Algol, wins the Turing Award. And when you win the Turing Award, they let you give a lecture. This is his. Can programming be liberated from the von Neumann style, a functional style, an algebra of programs? I love this title. I love the word liberated. I think we should use that a lot more in software. But what does he mean, the von Neumann style? Well, he basically means Fortran and Algol, which he helped invent, and this is his apology. Today, he would mean C. And what he's talking about is imperative programming, mutating some state step by step by step to get your program from one thing you have to something you want. And there's a lot of ideas in this paper. But the things that really fascinate me about it aren't what we think of as functional programming. Backus doesn't even mean, when he says functional programming, he doesn't mean what we mean today. He actually means a completely different thing. So that's not the important thing. No, what's important is that he says we can decompose complicated problems into simpler problems. We can transform those and make them generic, and then we could put them back together with rules, an algebra. That's what an algebra is. It's a set of rules for tearing things apart, transforming them, and putting them back together. Now, I want to be clear. Swift is not a functional programming language. Trying to make it one tends to lead to all kinds of headaches. Trust me, I know. But there are many, many lessons that we can learn from all the years and years of research, decades of research, that have gone on mostly in functional programming languages. So we're not going to talk today about immutable data or recursion or monads or applicative functors, none of that. We're going to talk about algebra, an algebra of programs. We're going to talk about composition. Now, building things out of existing and reusable pieces is better than building a new giant program every time you have a new problem. There are, the obvious benefits of code reuse, but really what's more important to me is comprehension. It is easier to understand small programs and reason about small programs than large, complicated programs, right? There are certain things when you encounter an enormous 45,000 file program, you just can't understand what's going on. I think most people today would agree with that. I don't think I've said anything controversial. In 1977, this wasn't a controversial statement either, right? Everyone already also knew about that too. So what's the point? I mean, we've all learned our lessons, right? We know composition is the way. We use delegates and protocols and keep our bindings loose. I mean, we don't build tightly coupled monolithic pieces of software like they did in the Fortran days anymore. Our classes do one thing, and they do it well. I know. This is composition, right? These are protocols. Discover View Controller is composed out of table view data sourcing and archive results updating and discover view model mode delegatingness. We got to put this stuff somewhere, right? An object that conforms to a bunch of unrelated delegates is not, or a whole bunch of unrelated protocols, is not composition. It's the opposite of composition. You took things that were intentionally split up into separate protocols and glommed them together into one giant object. I run into code like this a lot. You've got a table view, collection view, whatever, and it's got maybe a couple of states. You've got your logged in state, and then you get all your Instabook tweets. And if you're not logged in, you get this one please log in cell, right? That's maybe really tall, right? So you have in each delegate method, you check, am I logged in, and you do the right thing. And then it's not so bad, but you add searching. And then it becomes that. It's not too bad. I mean, we can work with this. We're programmers. we can work with this. And then they call you up and they go, hey, I want people who have never logged in to get some default content to get them started. But if they have trouble logging in, then they should see the error. But when they refresh, then they should get some cache content to keep them going. And that's when you go through the 7 stages of implementing a complicated feature in this code. There has to be a better way. Glad you asked. What if we used composition? I mean actual composition. What would it look like? Shocking fact. There is no rule that says that your data source has to be a view controller. I know that's the default. It's not a rule. You are free to make a class, an object, that is nothing but a data source. Well, so what does that mean I can do? That means that I could break it all up. I can have a browsing data source for the browsing state, and one for the searching state, and one for the not logged or the logged in when I need to log in state. And each one does one thing. It just serves cells for that state. There's no if logic, right? Do one thing, do it well. Now, I can't get rid of my if logic. It has to be somewhere. There's the rainbows. This is the magical rainbow app. This is what makes your app special. It's the craziness. It's the kind of human-centric side. Humans want weird things. They do. And it's not bad. It means somewhere in your program will be weird. You can't get rid of it unless you get rid of your users, which is a thing, but don't. But you can put it in one place. I'm not spreading it out all over the code. Okay. So we broke this into 3 data sources. I want to look at these first 2, browsing and searching. And they really feel like they're the same thing. I mean, one just has a filter on the other one. That's kind of actually, I could just say they both have a filter, and one filter happens to say show everything, right? That's a filter. Well, if I do that, if I think that way, well, I could build one thing, a fetch request data source, right? And now I can make it generic, right? That's kind of nice. Oh, wait. That's not going to work. It's never going to work. I mean, it's fine, but we can't reuse it. We know we can't reuse it because everyone knows this is how you configure cells, right? In cell for row at index path, you grab a cell, and you have line after line after line after line of plugging stuff in all the right places. And that's a lot of code. And you've tried to put that in a closure. That's never going to work. And you're right. That's pretty bad because this is not right. You've broken MVC. This is not model view controller. You don't understand correct composition in Cocoa. Most Cocoa developers I know, and most programs that I go into, kind of get this. They get the MVC paradigm, right? The controllers mediate between models and views. Yeah, I mean it. Controllers mediate, coordinate between models and views. That doesn't mean they tear apart models and stuff them into views. They coordinate. They get them together. Think about strings and labels. The model object for a label is a string. It's just this model object. But when I display a string, I have to tear it apart into characters and glyphs, and eventually all the way down to glyphs, and they all need to go to specific coordinates. So, of course, what we all do is in our view controller, when we want to assign a string to a label, we tear it down into glyphs, pull each glyph out, put it into the label at the correct place, right? No. You just hand the whole string, and you say, label, you know how to display strings, go do it. So why do we forget that when I have a person object and a person cell? Just give the person to the person cell. It's the same thing, right? Let the cell be smart about what it's supposed to be smart about, and let the view controller be smart about what it's supposed to be smart about. That's composition. And when we do that, then all this crazy, logic, complicated logic, suddenly becomes one line of code, right? I just say, grab it, stick it in. Well, that's easy. And as soon as I do that, I go, wait, I could make an associated type. I could make this into a generic, right? Or not, and I could say, I'll get a cell, and I'll just stick it I'll say get from my models, stick in my model. Now, now everything's reusable. Everything's generic, right? Everybody solves one problem. And when I think about that, I can think about my other one, my login data source. And that really is just a static cell data source, right? And maybe I can figure that by handing it a storyboard and an identifier, or maybe I create a cell and hand it and say just every time give it back to me, or whatever you want to do. But now I have another piece of reusable code. And when you do this, you can start to think about much more complicated ones. I could imagine a simple array data source that I hand array to and it hands me stuff. Or I could have a network response data source, right, that handles all the process of going out and coming back. Now that's going to be complicated because networking is complicated. But you can write it once and use it again and again. And it puts it in one place. New example. I get this question asked all the time. All the time. I've got this list of names and this list of ages, right? And I kind of want to sort them together. I'm sorry, it's that, right? Together. So that I sort the names, and when I get them in order, I want also ages to be sorted in order. And people ask this on Stack Overflow a lot, and somebody will always helpfully come along and tell them the solution. It's easy, easy. Well, you zip them together, and then you sort it into tuples, and then you sort it, and then you unzip it, and then they go, oh, yeah, right, there's no unzip in Swift, but that's okay, here it is, here's the little unzip, and easy. And then you add another array, right, for the user IDs, and you've got to remember to sort that one too. And every time you add a new field, you got to go back and remember all the little places that you touched all this. And every time you have insertion logic, you got to remember to insert them in the right order. And you have to deal with moving. That gets really complicated, right? And you finally get it all working. And you put it to bed, and you go off to do other things. And your boss calls you and goes, hey, could we sort by managers first instead of name? And then sort by name? Yeah. And you look at your code. What if we used composition? What if we turned it inside out? Instead of having many arrays of one property each, we could have just one array of structs, right? And it has many properties. See how I've turned it inside out? The mathy word for that, by the way, is a dual. We've created a dual. It's very nice. Instead of spreading that information all over the program, we've put it all in one place. And now when we add new fields, it doesn't matter. It's all easy. And what did we do? What did we create? We created a type. That's what helps us there. And instead of making it easy, we made it simple. A type. What's a type? Let's think about this thing of every value. You've got some variable of some type, and I want to think of every possible value it could hold. Everything. So for an int, there are 2 to the 64th possible ints, right? They can be held. And it's not infinite. I mean, it's not every int. People say, ints are integers. Well, no, they are the values between, in a certain range. There's a set of them. I can think about strings. Strings, I don't think there's a word for the number of possible strings, but again, it's some finite number of possible strings. It certainly is not every possible value. And I can even think about things like dictionaries. I mean, there are values that are dictionaries and values that aren't dictionaries. So again, I want to think about everything I could possibly put in there, and the program compiles. Now, then I want to think about the values that could go into this variable that make sense in this program, right? So say you have a state, and you have, loading, viewing, and editing. So there's 3 states, and you're going to store it as an integer, 0, 1, 2. So an integer can hold something like a quintillion values, and you're using 3. We're going to call that weak. If you're using a string, which, as I said, I don't even think we have a word for how many possible strings there are, and you're, say, holding, 20 keys, that is an insanely weak type. Now, that doesn't mean strings are weak. Strings can be strong. If I'm downloading stuff from the internet, any conceivable string could conceivably be on the internet. Therefore, that's the proper type. That's what I mean. But if you could count up all the possible legal values, then string is not being used in a strong way. So here's kind of the maybe counterintuitive part. When we want to make our types strong, we shrink them. We give them fewer values. Ideally, if we can really pull it off, we have exactly the same number of legal values as possible values. Those two things are exactly the same. Types do a little bit more than hold values. I said they're a named set of values, but they also add a thing we call context. One of the contexts that it holds are a set of invariants. These are things that must always be true in my program. So if I think about that list of names and ages, one of my invariants was all of the names and all of the ages will always be in the same order. They will create an order that is the same, that matches, and that they will all have the same number of elements. It would be considered a programmer error if I ever got into a state where those two arrays were different lengths. Okay. When I had a bunch of arrays, to enforce these invariants, I have to write preconditions, right? Or fatal, I have to put in these things that check for that at various places and crash the program if it doesn't work. Or at the very least, I have to write unit tests to check all those things. And if I don't write unit tests, I could just hope, right? But hope is not a great strategy for enforcing invariants. But when I turn it around and I have an array of structs, it is impossible to violate my invariants. The program wouldn't compile, right? There's only one array. It can't be inconsistent with itself, right? So I don't need tests to make sure. The more places that our types can hold illegal values, the more time we spend writing preconditions and unit tests to make sure that they don't. The more constrained our types, the stronger our types, the more whole classes of bug are actually impossible. They could just not happen. The compiler wouldn't let us go forward. So stronger types means fewer tests. I would rather have code that obviously has no bugs, that is so simple and so type constrained that the only possible implementation or the only possible way that it could work is correct, right? Nothing else would build. I would rather that's my ideal, than a program that I've tested a lot, and so I kind of feel like it probably is fine. What does that mean in practice? How do we do this? We have to look really carefully at our squishy types and make them stronger. I'm going to start with the squishiest type in Swift, which is any and any object. They're really close. There's not a lot of reason to separate them. And it is arguable whether the unsafe types are even squishier, but any and any object are pretty darn squishy. They can hold any value that Swift can talk about, right? It is rare that you mean that. I mean, you mean seriously, when you say, I take any, you mean literally, I hand you anything at all, you're cool with it. That's fine. Print comes to mind, right? Out of standard lib, print means it. You can hand print absolutely any value in the entire Swift type system, and it says, I'm good. That is rare. I can think of very few cases where that comes up. Now I know, Cocoa generates any. And it generates any in one particular place, JSON parsing. Can we talk about anything else except for JSON parsing? It's the only thing we talk about. But JSON parsing, yes, I admit, JSON parsing generates any. Because JSON is full of any. JSON is not full of any. Actually, any is a lie. There are certain things that are legal JSON and other things that are not legal JSON. There are certain dictionaries that make sense in JSON and other ones that don't. The problem is Cocoa gives you a lousy type for it. Don't fall for it. Fix it. You can fix it, move the stuff out of any and get it into something else, anything else, right? A class, a struct, an enum, something, an int. So, once you're done with the parsing, any should go away. After any, dictionary is probably the most abused type in Swift. And I'm not even counting dictionary of string to any object. We've already been there, because that's just doubling up. But a dictionary is an arbitrary. It means something. It is an arbitrary mapping of keys to values. Arbitrary. That means any legal key should be okay. You should feel okay with any key that is in that type. So let's look at this. This is really common. Dictionary has a key name, it has a key title. So my next dictionary line, I'm going to have dictionary, and the string will be the entire text of War and Peace. That makes sense. That makes no sense. The next line is going to be address. We all know the next line. The next line is going to be address or city or phone number. There's going to be a small set that it's going to be. It's not going to be just any old string. And you're going to go, oh, no, it's okay, Rob, it's okay, don't worry. I'm going to use string constants. Use a struct. When you use a struct, now all those problems go away. I don't have that problem. It's a stronger type. This use of string in weird ways has a special name. I didn't realize this was its special name until recently. It's called stringly typing. This shows up, actually, and what's funny is this shows up in every language. Every language complains about stringly typing. I thought it was just us. Let's think about this code. You're switching against start and end. And then you have a fatal error, because you need to check the default case, because maybe it's not one of those. And again, you go, no, Rob, I'm going to use string constants. It's fine. String constants fix nothing here. Nothing. That's not the problem. The problem is fatal error. You just put a line of code in that should never run. Why would you want a line of code in your program that both should never run and if it does, crashes? I don't want that. That's bad. No, you want here an enum, right? Then all of a sudden I don't need default. It just works. And you go, oh, but I need to be able to see them as strings. It's fine. Swift can do that, right? But I don't have to have fatal error. Every time you find yourself writing fatal error or anything else along that line that's going to crash the program, you should be thinking, could I have better specified what I have in a type? How about lowly int? So yes, ints sometimes are used when enums should be used. True. I don't want to talk about that. First off, I find that most people get that. Most folks, when they have ints that should be enums, they use enums. Swift makes it pretty easy, and most people get it. It's no problem. And that works when there's a fixed set of values. But what about this? So, and this comes from my code. This actually is what precipitated half of this talk, is this little structure I had. It had a few more fields. But it had an ID, and I had this ID that was an int. It's an identifier, right? Unique identifier. That was an int. And what happened is I wanted to switch it to be a string, because we were going to do things a little bit differently, and I wanted to use a string there. And I had to walk through all of my code looking for all the places I'd used ints to see if it might have been an identifier. That's a lot of places. The more I thought about it, though, yes, that was very frustrating. But it was worse than that, because is there anything numberish about identifiers? At the time, they were implemented as numbers, but can I add them? You can't add identifiers, but I can add ints. Can I divide them? That's insane. That doesn't even make sense. No, what I can do then is I lift. I give context, and I turn my identifier into an identifier. I give it a type. Right? Now, all of a sudden, you can't add IDs, right? That's prevented. And when I wanted to change the value type to something else, I wound up having to change, I think, 3 places in the code. And the compiler told me exactly which 3 places they were. That's what I get with a stronger type. Now, not all things in Swift are types that look like types. One of the weird ones is protocols. Protocols are not really types. Call them type-ish. They're type descriptions. They tell you what a type would be, what kind of type I want. It's important that we understand that they're not exactly the same, because I want my types to be strong, but I want protocols to be weak, very weak as I can get them, right? Because say I have a protocol that only has one requirement, right? Has this one line like custom string convertible, just you have to implement description. Well, that's really nice. We like those kinds, right? But that means, in principle, huge numbers of values could be of that type, or of that protocol, right? Huge numbers. Well, that means it's weak, right? And that's good, but that's good. I like that. I don't want to make lots of constraints on my protocols. I want lots of things to have them. I want them to be easy. So I don't want to create restrictions I don't need. What about generics? Generics are funny because they're not types. They are functions that generate types. It's weird because in Swift, the syntax can confuse you, but they take a type parameter and they return a type. It happens to run, these types happen to run, or these functions happen to be evaluated at compile time, but that actually doesn't change much, except one big thing, which is while they are functions, they are not first-class functions. In Swift, we can have first-class functions, right? We can hand around functions as a thing, but not type functions. They're not first-class. We can't talk about an array, just an array, nothing else, right? And some languages you can. That's not absurd. It's a feature. It's called higher-kinded types. And you'll see people talk about that sometimes. I wish Swift had higher-kinded types. What would that mean? Take this function. This is illegal. I can't do this in Swift, right? I have to add a type parameter. Why? I don't use t anywhere. Why do I have to pass it? This gets worse if I stick it in a structure. I can't have this. I have to, not only do I have to have a type parameter, but it escalates. All of a sudden, lots of things become generic, or nothing needed to be generic. So that's frustrating, right? We can get around it. There's type erasers. There's weird little boxes you can use. But it restricts what you can say. It constrains the kind of solutions we can write, or at least that are easy to write. What you can say influences what you can imagine, and what you imagine controls what you can build. That's why I'm bothering telling you all this, right? Teaching you weird vocabulary. A lot of this stuff is type theory and the like. It's because when you can imagine a better type, when you know that such a thing could exist, maybe it doesn't exist in Swift, but you know it could exist, then all of a sudden, you start looking for ways to solve that. And maybe you can't do it as beautifully as you'd like to, but suddenly you can build things that make whole classes of problem trivial. Let's get back to a practical version, right? We're going to try to change this around and fix its shape. We've got this thing, it fetches something, and when on completion it gets maybe a string, and maybe an error. What the heck? This is horrible. The horrible part is this, maybe a string, maybe a string, I don't know what that is. What does that mean? Well, I'll fix it. I'll put labels on it. This is worthless. This is totally worthless. This is a comment in Swift. This doesn't actually have any influence. You could put any strings you want there, and when people call it, they can change it to any other strings. These are just labels. They mean nothing in Swift. So that's not great. There's this other problem, though. I have name and address and error. How are name and address and error all related? How do they fit together? The answer is they don't. Name and address kind of seem to fit together, and error is something completely different. I wish I had a way to say I want name and address. I want a grammar. I want a type language where I could say the word and. And we have that. It's called a struct. A struct, we call it officially a product type. Why do type theorists call it a product type? Well, how many values are there of it? When I have a struct of style and I say I have 3 colors possible, and I have 2 possible thicknesses, how many possible styles are there? There are 6. And that's the total number of possible values that struct can hold, because it is a value. The whole thing's a value. Okay, so I'm going to use an and type, and I'm going to create this thing, maybe a person, and maybe an error. Now you see, I'm saying and. I'm still saying and. That's because a tuple is also an and type. They're very, very similar to like an anonymous struct, so they have the same rules. But, I mean, I like that. That's pretty good, because I can just read off. I don't need labels. Notice how no label problems. But it doesn't make much sense. I mean, I don't know if you can see this. Not all of the cases make sense. What if I have a person and an error? I mean, both of them show up. Is that legal? I don't know. What about neither? Is that legal? Do I have a fatal error? Do I ignore it? I mean, you have to think about it. I hate to think about it. Why would I do that? No, because I don't mean maybe anything. I mean a person or an error, one or the other. We want another type. How do I say or? Enums. Enums are or types. For the same reason that product types are product types, or types are sum types. How many possible styles are there? There's one kind of line, there are 3 kinds of squares, there are 4 kinds of styles, right? Sum type. Okay, that's nice. So now, I want to be able to say that. I want to be able to say person or error. I'd like to make it kind of generic, and I'm going to show you this because this is the common way people who are used to this kind of thing do it. We all create the same type called result. We all wish that Swift had it built in. There is much debate as to why it is or isn't, but you can build it in 4 lines of code, so please do. And I build these all the time. Don't think you need a big library. I mean, I just build them. It's okay. They don't cost anything. But now I have a successful value or a failing error. Context. Again, context. So where does that leave us? Instead of this string, maybe, I have a resulting person. Now, you do need to learn that resulting means could fail. But other than that, everything's right in the signature. I don't need comments. I don't need labels. And that's what I want. And the compiler is going to enforce that I do it all right. And that's the lesson of functional programming that I think we should bring to Swift. Complicated things can be broken down into smaller, simpler things. And we can find generic solutions for those simpler things. And then we can put them back together with rules and composition. And when we do that, the compiler can make all kinds of bugs impossible. And that's a lesson that I think that both John Backus in the 70s and Krusty today would both agree with. Break it down, build it up, learn from our elders. Thank you.